Hello everyone and welcome back. My name is Mr. Koval, and in this video I'm going to go over standard heats of formation. So what are heats of formation? Heats of formation is the amount of energy that's released or absorbed during the formation of 1 mole of a pure substance from elements in their standard states. So this is by definition the formation of exactly 1 mole of the substance, and you're forming them from their elements in their standard states. And so, standard states are defined by the scientific community as having being, for example, if you're talking about solutions, it's 1 mole. 1 molar solutions is the standard for solutions. 1 atmosphere of pressure at 0 degrees 0 degrees Celsius temperature. So those are what is meant by, say, standard conditions. So, for example, is what's the state of oxygen under these standard conditions? It would be a gas. For carbon, it's graphite. Sorry about that. So graphite would be the standard state for carbon, not diamond, right? So things like that. So if you're forming a pure substance or a compound from its standard states, then there's going to be a certain standard heat associated with that particular formation or that particular reaction. Um, Under these standards, the actual elements themselves in their standard states, their standard heats of formation are zero. And so when we write an equation, we're writing the equation for the heat of formation so that 1 mole of the product is formed. So example, here is an example of a reaction for the formation of carbon monoxide. So here, we're forming exactly 1 mole of the product. And so in order to have the proper equation, and that fits with the definition of the heat of formation, because remember, the definition is that you're forming 1 mole of the pure substance. So here I have 1 mole of substance. In order to have this, then I need a fraction for my coefficient. This is pretty much the only time where fractions in your coefficients are allowed, because we're trying to have a heat of formation equation here. So 1 mole of carbon graphite plus a half a mole of oxygen will form 1 mole of carbon monoxide. So for this reaction, the standard heat of formation is negative 99 kilojoules per mole. This little circle up there means standard. The F means formation. So this is referring to the change or heat for the standard heat of formation for this particular reaction. So I said in another video that there are different ways of finding the heats of reaction or the standard heats of reaction, or what is also called the standard enthalpy of a reaction. And so I mentioned bond energies before. So if you know the bond energies of the different bonds in your reactants and products, then you can sum up the number of the amount of energy that it takes to break the bonds in your reactants and the amount of energy it takes to form bonds, that the amount of energy that's released when you form bonds in your product, and then you find the difference between the two. That would be the heat of your reaction. Another way is to actually use the heats of formation. So if you know how much energy is absorbed or released in the formation of your products and reactants, then you can find the difference between the reactants and the products, and that would be the heat of the reaction, or the standard heat of reaction, or what is also called the standard enthalpy of reaction. And so that comes down to an equation. So here is the equation to find the standard heat of a reaction. So you can take the sum of all of the molar amounts of your products and multiply them by their standard heats of formation. So this n here refers to the coefficient, or the molar amount that is in your balanced equation, and you're going to multiply that coefficient or that number of moles by the standard heat of formation that you would look up in a table. So you're not going to memorize these. They would have to be given to you, or you look them up in a table and you use them. So the sum means this is a sigma. This is a capital Greek symbol sigma. This is used in sum for those of you who have taken calculus. You know what this means. You probably have heard of Riemann sums and that sort of thing. So this here stands for a sum, or adding together. So I'm going to take the coefficient of one of my products. So here I'm taking a product. So let's say I have two products. I'm going to take the coefficient or molar amount in the equation and multiply that by the standard heat of formation of that product. And then I'm going to add to that the next product. So if I have two products, I'm going to take the first product, multiply its coefficient by the standard heat of formation of that product, and then add to that the multiplication of its coefficient, the coefficient of the second product multiplied by its standard heat of formation. I'm going to add those together, and so that's the sum of the standard heats of formation of my products. And then I'm going to subtract from that the sum of the reactants. So again, if I have multiple reactants, I'm going to take the coefficient in the balanced equation of one reactant, multiply it by its standard heat of formation that I look up in a table, and then I'm going to add to that the next reactant. I'm going to multiply that reactant's coefficient moles by its standard heat of formation, and do that for all the reactants, sum that together, and then I take the difference. So it'll be products minus reactants. And so you can use this equation to help you to calculate the standard heat of a reaction. So let's do a couple of examples to see how this works. Okay, let's go over a couple of examples. So here I have the equation for calculating the standard heat of a reaction from the heats of formation of products and reactants. And so let's look at question number one. So problem number one is calculate the standard heat of a reaction for the combustion of methane CH4. So here we need the balanced equation. So here's our balanced equation for the combustion of methane. And so we're going to use this equation. So we're going to use the coefficients to help us calculate the amount of energy for products and reactants. So here we have the standard change in enthalpy of a reaction. Again, it's going to be the sum of the heats of formation of products minus the sum of the heats of formation of reactants, both multiplied by their molar coefficients in the balanced equation. So here, this table here, I'm going to be using for the first reaction. So again, you're not going to memorize these. You look these up in a table. And so here I'm going to do, again, products minus reactants. So first the products. So we have CO2, carbon dioxide. So carbon dioxide has a standard heat of formation of negative 393.50 kilojoules. And so I have a coefficient of 1, so it's going to be 1 times negative 393.50 kilojoules. So this comes from the carbon dioxide. And then I'm going to add to that water. And this is liquid water. So in the table, I would look up liquid water. And so water has a heat of formation, or liquid water has a heat of formation of negative 285.83 kilojoules. I have a coefficient of 2 moles, so that's going to be 2 times negative 285.83 kilojoules. So both of these are added together, subtracting out the sum of the heats of formation of the reactants multiplied by their stoichiometric moles in the balanced equation. So then I'm going to subtract, here are my reactants, So I have first reactant is methane. So methane is negative 74.80. So I only have a coefficient of 1. So that's going to be 1 times negative 74.80 kilojoules plus, and then I have oxygen. I have 2 moles of oxygen, but you'll notice in the table that the heat of formation of oxygen is 0. And as I said before, elements in their standard states are going to have a standard heat of formation of 0. And so that's what it is in the table. And so I have 2 times 0 kilojoules. When you do the math, you end up with, you end up with a heat of reaction. The standard heat of reaction is negative 890.36 kilojoules. So this is the amount of energy that's released. So it is exothermic because I know that because there's a negative there, which means heat was released, it lost energy. So the reaction is exothermic. So this is the amount of heat released. So that's the standard heat of reaction calculated from the heats of formation that are tabulated. Okay, so that's problem number 1. Let's look at problem number 2. So problem number 2, similar to problem number 1, instead of methanol, I'm given ethanol. Ethanol is used as an additive in many fuels. So the reason for that is to keep the what is called to avoid knocking in your gasoline and get a more cleaner burn. So the question is, what is the standard heat of the reaction in kilojoules for the combustion of ethanol? And here's the balanced equation for the combustion of ethanol. And so again, we're going to use our equation, the sum of the heats of formation of products multiplied by their stoichiometric coefficients, subtracting the sum of the heats of formation, standard heats of formation of reactants multiplied by their stoichiometric molar amounts in the balanced equation. So same as before, we're going to start with our product. So I have 1 carbon dioxide. Oops, I forgot to balance the equation. So this should be 6 moles of oxygen forming 4 moles and 6 there. And so this is my equation. Now, notice that the coefficients here are not in their lowest whole number ratio. So you can reduce that, but it doesn't matter. It would come out to the same number anyway. So, so here, given this reaction, well, it's not going to come out to the same number since you kind of doubled everything. So then this number here would end up being double the amount of what it normally was because you're doubling the amount of the reactant reaction. But the process is exactly the same. So here I'm starting with my product. So I go to my reaction. So here I have my products. 4 carbon dioxide. So again, I go to my table. This time I'm using this table, which the numbers are pretty similar, except now I have ethanol in here, so I'm going to use ethanol. I want to point out here in this table I have water gas and I have water liquid. And notice that there is a difference in the heat of formation, the standard heat of formation for both of these. So make sure you double check your reaction to see whether water is a liquid or a gas, and then make sure you use the right heat of formation. So I have my first product is carbon dioxide. I have a coefficient of 4, so that's 4 times minus 393.5 kilojoules. So that's my carbon dioxide. And then I'm going to add to that my other product, which is liquid water, and I have a coefficient of 6, so that's going to be 6 times. And then liquid water is negative 285.8, so I have negative 285.8 kilojoules. So all of this added together, and then I'm going to subtract from that the sum of my reactants. So here, my first reactant is ethanol. So I have 2 moles of that. So it's 2. And then multiplied by the standard heat formation of ethanol, negative 277.6. So negative 277.6. So this multiplied and then added together with oxygen. And again, oxygen is 0. So that's going to be 6 times 0, which is 0. So that's not going to be added. And so when I do the math, I get a delta H of the reaction equals the negative 2,734 kilojoules. So that's for this reaction. So if I was to reduce the numbers here, right? If I was to divide everything by 2 to get the coefficients into their lowest whole number ratios, then I would have to divide this in half or divide this by 2 to get the delta H, the standard heat of formation for that reaction, where the coefficients are reduced. So this heat of formation is per reaction. So here this is double the reaction. So I doubled, this would be double of that. So I hope that makes sense. If this video was helpful, if this makes sense or helped you in any way, by all means, please like the video, share the video, hit that like button over here somewhere. Make sure you subscribe to my channel. Hit that notification bell. When you do, please click all so you can be notified by all the videos I put out. And finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I'd love to hear from you. Thanks for joining me and have a great day.